Section 1.4 next, predicates and quantifiers. So now, things are getting more complicated. We're including variables in our logic statements. So here's x. And so if we say x less than or equal to 10, see, we saw before that's not a proposition. It's not true or false. Well, you need to know what x is. Okay, and so this less than or equal to 10, that's called a predicate. It's saying something about x. But if you know what x is, then you do get a proposition. So if x is 3, then 3 less than or equal to 10, that's true. But if x is 12, 12 less than or equal to 10, that's false. Okay, so if you know what x is, then it becomes a proposition. And we can make a propositional function. So p of x says x is less than or equal to 10. And the idea is that p of x is going to be true or false depending on what x is. So we saw already, p of 3 is true. P of 10 is true, 10 is less than or equal to 10. But p of 17.6 is false. Okay, if you put in 17.6 for x, then this whole thing becomes false. 17.6, that's too big. It's not less than or equal to 10. We'll be looking at functions more in chapter 2, but the idea is, this is a function, so it depends on x. We're not multiplying here. This is function notation. So x is an input. Alright, so for different numbers going in here, you get true or false. Some more examples. Suppose p of x says x squared equals 9. Alright, so another propositional function here. It's saying something else. Well, if x is 0, so if the input is 0, is that true or false? Is 0 squared equal to 9? No, that's false. So p of 0 is false. But if you put in 3, 3 squared equals 9, that's true. Also negative 3 quantity squared is also 9, so that's true too. So if you put in any number for x that's not 3 or negative 3, it's going to be false. Example 3, a different type of function. Q of x says x is a country. So the inputs here are not necessarily numbers. So if you put in India, Q of India, well, India is a country, so that's true. But if you put in a day of the week, you'll get a false output. Yeah, there's no country called Monday. Okay, so yeah, we're using these functions. This is function notation. So things go into the function, and what comes out here is either true or false. Okay, yeah, more examples in the book. Okay, so we're in, section 1.4. Okay, example 5. We're setting up this propositional function of 3 variables. So this R takes 3 inputs, x, y, and z. And so R denotes this statement, x plus y equals z. And so example 5, what are the truth values of the propositions R1, 2, 3 and R0, 0, 1? Okay, so for R1, 2, 3, so x is 1, y is 2, z is 3. And we get the statement 1 plus 2 equals 3, and that's true. Okay, so R of 1, 2, 3 is true, but R of 0, 0, 1, well, that's saying 0 plus 0 equals 1, that's false. Alright, so yeah, these propositional functions, so for different inputs, you're getting true or false, depending on what the proposition is saying. Example 6. Okay, we have this statement. So this is something you might read in a computer program. If x is greater than 0, then x colon equals x plus 1. Yeah, this colon equals, this is important. This is the assignment operation. So you're assigning x the new value of x plus 1. So this increases x by 1. Okay, so when the program executes this line of code, well, it's going to do it's only going to carry this out if x is greater than 0. So for example, if x is 3, okay, so if x is 3 and we get to this line, then this is true. So then we carry out this statement and x turns into 4. But if x is, say, 0, then this is false, and then we don't increase x by 1. So x stays at 0. Alright, so this is a very common if-then statement. Okay, next let's get into quantifiers. Suppose you say all sheep are white. So the quantifier here is all. It's you're saying something about sheep. They're all white. All of them are white. Okay, so this should be true or false. Which sheep are we talking about? Are we talking about all sheep in the world, or maybe let's just talk about 4 sheep you see in a field? Okay, so we're labeling these sheep S1, S2, S3, S4. We're using set notation. We'll talk about this in chapter 2. Okay, so now we're being more specific. So our statement, all sheep are white, now we're just referring to these 4 sheep. All right, so that's our domain of discourse, or our universe of discourse. It just means what we're talking about when we say all. So in this case, all just means these 4 sheep. That's our universe. That's our domain for this example. And we can make this use our logic. So set this up as a propositional function. Let wx. W of x says x is white. Okay, so when we're saying that all sheep are white, so that means S1 is white, and S2 is white, and S3 is white, and S4 is white. So we can write that like this: W of S1 and W of S2, S3, S4. Okay, so we're using the AND operation, conjunction. All right, so is this statement true? Well, okay, you take a look at the sheep. Yeah, they're all white in this field, so this is true. So your statement, all these sheep are white, is true in this case. 4 white sheep. Okay, but there's another way we can say this. We have this special notation. So for all x in a domain, we have this notation. It's like an upside down capital A. So this means for all x. Like A for all. Okay, so we can use this notation for all x. Wx means for all sheep in the field, Wx, they're all white. Okay, example 4. Suppose you change your domain of discourse to a different field with 99 white sheep and 1 black sheep. Okay, so for this domain, then for all x, Wx, that'll be false. Okay, so it's not true that all these sheep are white. there's one black one. Okay, so it's important to understand what this means, but also this is we're making a new proposition, so this is going to be true or false. Okay, example 5. Let's get back to numbers. Let p of x say x squared plus 3 is greater than or equal to 0. Okay, so is for all x, p of x true or false? Where the domain we're talking about here is the set of all integers. Alright, so let's maybe try out some integers just to get a feel for the problem. So, for example, when x is 0, is p of 0 true or false? Well, if you replace x by 0, you're getting 0 plus 3. 3 greater than or equal to 0, that's true. And so p of 0 is true. And yeah, if x is any positive number, this is going to be true. But also if x is negative, since when you square a negative, like negative 2 squared is 4. So this will be true in that case. Yeah, so x squared, this is the smallest this can be is 0, and if you add 3, the smallest the left side can be is 3. Alright, so this statement's going to be true for every integer x. Okay, so this is true. So for all x, for all integers x squared plus 3 is greater than or equal to 0, that's true. So this statement is true. Alright, so this upside down a is called the universal quantifier. And this statement for all x, p of x, is called the universal quantification of p of x. And it just means for all x in the domain we're talking about, we have p of x. Okay, so yeah, if p of x is false for an x in the domain, then that's called a counterexample. So that if we have any counterexamples, then that's going to make this false. Like a black sheep showing up. All right, so that's our universal quantifier. Okay, there's another quantifier with a different symbol. So this is like a backwards E. E for exists. So this symbol is called the existential quantifier. And this statement is the existential quantification of p of x. And the way to read this is there exists an x in the domain so that p of x. Alright, so now we're worrying about existence instead of for all. Example 6, let q of x say x squared equals 3. then what is the truth value of there exists x so that q of x, when the domain is the set of all real numbers? Okay, so as x runs through all the real numbers, so does there exist an x to make q of x true, to make x squared equal 3? Alright, so yeah, if we try to solve this equation, take square roots, or use the square root property. So there are real number solutions. The square root of 3 we're looking for, or minus the square root of 3. Okay, so there does exist a real number x so that q of x is true. Okay, so this proposition is true. Yeah, really we're looking for solutions to this equation. Yeah, there is a real number solution. In fact, there are two, but for this to be true, we just need one solution. Maybe an easier example. 7, you see 3 apples, a1, a2, a3. Let r of x be the propositional function that says x is red. Okay, then for this domain of 3 apples, so just these apples, for all x, r of x, so that's saying that all the apples are red. That's logically equivalent to the first apple is red, and the second apple is red, and the third apple is red. R of a1, and R of a2, and R of a3. Alright, so the universal quantification of r here is just saying, yeah, all the apples are red. But here we have the existential quantification of r. So there exists an x so that r of x. Okay, so this is saying something different. This is saying at least one of these apples is red, so there exists a red apple in this set of 3 apples. In other words, the first apple is red, or the second apple is red, or the third apple is red. R of a1, or R of a2, or R of a3. So for a red apple to exist, we just need at least one of them. They don't all have to be red in this case. Alright, so when you talk about all the elements in the domain having a property, then that's really, you're talking about the AND operation. But when you're talking about existence, then that's the OR operation. Alright, I hope that made sense. Okay, yeah, these are our two quantifiers. So for all x, p of x, so this statement is going to be true if p of x is true for every x. It's going to be false if there's a counterexample. there exists x so that p of x, well, that's true if you can find just one example where p of x is true, but it's false if p of x is false for every x. And so you can't find any examples. And so if all your apples were green, then there exists an x so that r of x, that would be false. And so example 11, let p of x be the statement x squared is strictly less than 10, and the domain consists of positive integers not exceeding 4. So that means 1, 2, 3, and 4. So for all x, p of x, okay, so for the numbers 1, 2, 3, and 4, is this always true? Well, 4 squared is not less than 10, so 1 squared, that's okay, 2 squared, 3 squared, but when x is 4, this is not true. So for all x, p of x is false in this case. So for the numbers 1, 2, 3, and 4, this p of x is not always true. Okay, so for x equals 4, that's the counterexample in this example. Okay, how about this example? N of x says computer X is connected to the network, and the domain here is the set of all computers on campus. So then the statement for all x, n of x, so what is it saying? It's just saying that, it's saying that all the computers on the campus are connected to the network. All right, and that statement, it's going to be true or false, depending on the if the computers are all connected. Okay, more examples. Here's one with existence. So if p of x is the statement x is greater than 3, what is the truth value of the quantification there exists x, so that p of x, where the domain consists of all real numbers, okay, so can we find a real number x so that x is greater than 3? Yeah, you could take x equals 4 or x equals 400, so yeah, they definitely do exist numbers x that make p of x true. Okay, so then this statement, there exists x so that p of x is true. And yeah, they're saying here, the only way this whole thing could be false if there are no solutions, if there are no x's that are greater than 3. So yeah, an example like that, example 15, let q of x say that x is equal to x plus 1. The domain here is the set of all real numbers. So what is the truth value of the quantification? There exists x, so that q of x. So are there any real numbers so that x is equal to x plus 1? No, so you could try maybe 0. So is 0 equal to 0 plus 1? No. No, so yeah, if you add 1, you're always getting a different number. So q of x is always false. Okay, so there exists x, so that q of x is false. Okay, so there's no solution here, so there does not exist any real number so that x is equal to q of x. X is equal to x plus 1. All right. Yeah, one more quantifier. Yeah, this is not as common as the other two, but just to mention it. So existing with a exclamation point. So this is the symbol for the uniqueness quantifier. Okay, so the way to read this is there exists a unique x in the domain so that p of x. Okay, so now we're just looking for, so for this to be true, there has to be just one x in the domain where this works. Example 8, find the truth value of there exists a unique x so that p of x, if p of x says 4x is equal to negative 12, and the domain is the set of all integers, alright, so we're really asking, is there a unique integer solution to this linear equation? Yeah, so you can see the answer, the solution is negative 3, and yeah, there's only one solution and it is an integer, so that means this statement, this uniqueness quantification is true. There does exist a unique solution. Alright, so last example, 9. Let q of x say x is a member of the US Senate. Okay, here the domain, let's say it's the set of all people living in the US. And let's decide if these quantifications are true or false. Okay, so part A is saying for all x, q of x. Okay, so for all people, all people living in the US are members of the US Senate. No, so that's false. Yeah, so for example, yeah, I'm a counterexample. I live in the US and I'm not a member of the US Senate. Okay, so Part B, there exists an x, so that q of x. So does there exist a person living in the US that's a member of the US Senate? Yeah. So there are 100 senators. So any of those would be an example of somebody existing who's a member of the US Senate. So this one's true. And the last one, so it's saying there exists a unique x, so that q of x. So is there just a unique person living in the US who's a member of the US Senate? No, so senators not unique. There are 100 of them. So we don't have uniqueness. Senators exist, but not unique. So this one's false. Alright, so again, we're quantifying members of the US Senate. Okay, so that's predicates and quantifiers.